So I will make a claim in this lecture that the elementary row operations do not change the rank of a matrix. And actually it's quite easy to see. So let's say the first elementary row operations, right? It was interchange of rows. Let me also draw a matrix just here. So let's say we have an m by n matrix A11, A12 till A1n, and then A21, A22, A2n, and it will have m rows. So the last entries for the last row will be am1, am2 dot amn. So if you interchange two rows, so let's call this A1, the row vector first, and the second row vector A2, and so on and so forth. So if you interchange rows A1 and A2, clearly the maximum number of linearly independent row vectors for A will not change, right? So hence, for elementary operation 1, that is interchange of row, the rank does not change. All right. The second is multiplying a row with a non-zero scalar, right? With a non-zero scalar. And again, that's easy to say. So let's say if I were to multiply the row vector A2, that is this entire row here, with a non-zero scalar, say C. Okay. So now my row vectors would be A1 and then CA2 and A3 and then dot AM. Clearly, again, this set of vectors will again have the same number of linearly independent vectors as this set, right? A1, A2, A3 till dot AM. So again, multiplying a row with a non-zero scalar really does not change the rank of the matrix. So again, tick here. And the third one is again very simple. So the third one is basically you replace, let's say, let me write it down in symbol. So you replace the jth row with, let's say, AJ plus C times AI, right? So all you're doing is essentially you're replacing one of the row vectors here, or one of the vectors here. Let's call it A3 in fact. So what would you do in this case if you apply the third rule is that now A1, A2, and the third vector here, the third row becomes A3 plus C times some other vectors. Let's say A1, and then A4, and then dot till AM, right? And again, you can see that the maximum number of linearly independent vectors here for this set here is the same as for this set. So again, the third operation also, the third elementary row operation also does not really change the rank of the matrix, and that leads us to a really super cool, awesome result. And remember that we discussed something called row equivalent matrices, right? Let me write it down. So we discussed in the last few lectures that something called row equivalent matrices, right? And these matrices are obtained by applying a finite number of elementary row operations to a matrix. Okay, and we have just seen that if you apply elementary row operations to a matrix, the rank does not change. And combining this result and this, what we know about elementary row operations, we can write down a really cool result. And the result is that row equivalent matrices have the same rank. All right. And this is really cool because now what you can do is that if you want to determine the rank of a matrix, all you can do is to reduce that matrix to row echelon form using the technique of Gaussian elimination. And you know that this operation will leave the rank unchanged, and hence now you can easily identify the number of linearly independent rows of a matrix or columns of a matrix, and say or figure out what the rank is. Okay, so to end this, let me just give you an example. The example is really small, or really not very complicated, but just illustrates the point I'm trying to make here. So let's say I consider this this example. So let's say vector a be 1 0 1 2, and let's make this 1 1 1 2, and let's make it 2 0 2 4. Okay, so now if you were to actually if I were to tell you, hey, go ahead and find out the rank of this matrix. So the first thing you can do is that you can actually apply Gaussian elimination to reduce it to a row echelon form. And I'll not repeat the process here. I think we have talked about it in a lot of detail. But so this becomes the pivot element. First row, the non-zero element, this guy 1 becomes a pivot element, and the game is to actually eliminate all these guys here. So we can do that by keeping the first row intact, 1 0 1 2, and we apply row 2 minus row 1, row 2 minus row 1, okay, and row 3 minus 2 times row 1, okay, and that will leave you with 0 1 0 0 and 0 0 0 0 all along. And now you can easily see that there are two linearly independent vectors here, right? And hence the rank of A is equal to 2. So alright folks, so that's all I had to talk about in this lecture. I'll see you guys in the next lecture.